This presentation reflects work by my whole team. At JPL, we have some cloud folks on it. We have some data analyst folks. It takes a team to put this work together. So I'm representing the work from all of them. So I'll talk a little bit about the file observatory, some of the backend updates we've been doing. We'll talk about it at various scales, feature extraction, user interface stuff. The bulk of this talk will be on descriptive statistics we have on a month of common crawl data. It's about 8 million PDFs. And then I'll end with next steps. So first, file observatory, why? The point of this, we developed it as part of a DARPA project on developing safer parsers with an initial focus on PDF parsing. We needed to enable performers to have access to lots and lots of PDFs from the wild so that they could test out their tools and potentially, for those who were interested, try to induce grammars from PDFs in the wild. So we had lots of technical reasons for having a heap of PDFs. The goal of the observatory is to try to make sense of that data at various levels and be able to search it, be able to index things rapidly, be able to do aggregations, group bys, roll-ups to make sense of what's in there. So the uses for this amount of data and the analytics we can do on it are quite varied. The initial goal obviously was just gathering the data so that we had enough for parser developers. The addition, of course, is that when you have 8 million PDFs, it's kind of like nature's fuzzer. The internet is nature's fuzzer in that you have crazy amounts of, large amounts of files that can do stress testing on parsers. You can look for timeouts, exceptions, all those other fun things, crashes. So it's really an enormously useful resource for testing parsers. Market analysis, if you trust the distribution of the PDFs, you can figure out who the producers are, in what regions of the world, when. Security analysis, obviously with so many PDFs, you can find lots of fun things in there. The file observatory, not necessarily on this corpus, but can be used for corpus characterization or digital preservation assessments if you want to look at versions of PDFs, at subsets of PDFs, how many PDF-A do we have, what types of PDF-A do we have, those kinds of things. And then also, of course, once one gathers this much data, one can apply machine learning, perhaps for creator tool attribution or other things that are fun to find and can be useful from a business perspective to find from a machine learning perspective. So lots of reasons for the software around the file observatory, but also for gathering this much data. So this is the overall view of the notion of the file observatory, which is we have a bunch of different data sources. We throw a bunch of different parsers against those files. We store intermediate results in a database and then make that all searchable via Elasticsearch. One of the things that we've been working, just as a side note, this was the initial version, but to make it more scalable, to make it more easily transitionable, we've moved away from cutting edge Amazon Web Services, AWS tools. Initially, this was done with Amazon Batch, Amazon Kinesis, Amazon Athena. We're now moving towards smaller hybrid things that can be used on the laptop or in the cloud. And I can talk about that in much greater detail later. So one thing we do, obviously, is after we run all of these tools, is we extract features from those to make those searchable and aggregatable and countable. So here's an example of standard out from PDFinfo, and we can take those various fields, put them into, take those various bits of information, put them into individual fields so that we can do roll-ups on that data. We've also done some more substantial feature extraction from QPDF's JSON format. That allows us to get what keys are in PDF dictionaries and do counts on those, allow advanced users to search on that kind of information, what kinds of combinations of parents and keys types, if a PDF object says that it is a pages type, what kind of keys do we have in that? Key value pairs, which can be extraordinarily useful to find out different values for common keys, what kind of filters are being used, maximum filter count, all sorts of things. The key thing about all of this is that the goal is not to do a massive grep or a PDF grep on these features, but it's to index the fields that people want to search on or make sense of, and then allow the search systems, Elasticsearch, OpenSearch, or SQL to enable analysis on those. All right, so we've made some dramatic improvements to the front end since our last talk. This was based on, as we evolved more feature extraction, we realized that free text search wasn't quite the thing that was useful. There was typically a starting point, but really we wanted to make the facets much more easy to use and so on. So we've done that. In this slide, complex, we've added a number of different visualizations to allow different ways of looking at the data. When we have 8 million PDFs, trying to do even a scatter plot on that many points is a little overwhelming for the browser. So we now have random sampling to allow for easier, faster visualization, more real-time type visualization, and so on. We also have a geo component so that if you have geotagging for your files, you can put those on a map, and that's a really handy way to see what the distribution of your files are. So that's kind of an overview of kind of where the software is, the back end and front end. Lots of work has been going into that. We have about a year left, a little bit less than a year left on the project. So at this point, we're looking to move into documentation and getting public release for a number of these components. Many of the back end things are available currently on my personal GitHub site, but a lot is still in transition. So I wouldn't encourage folks to go there and get stuff instantly. All right, so CC main 2021-31. So this is a 1 month of Common Crawl. Common Crawl is an open crawl of the web that runs roughly every month. I have some stats on it. It pulls down a huge amount of data, largely HTML. It does include binary files, though. So we have that available. We've also published some bug tracker crawlers. We wrote crawlers to pull down attachments to bug crawlers. So we have what Peter Wyatt's calling a stressful PDF corpus. So that's a really nicely concentrated set of 30,000 PDFs. I think that's grown a little bit since these stats were taken, that have caused problems for people, and they've put them on open source bug trackers. We found this to be a really densely packed set of stressful PDFs. So Common Crawl, massive set of data. There are no very clear limitations. One, it's not the whole web. It's a convenient sample. It's whatever Common Crawl could easily crawl and gather. We also recognize that PDFs on the web can have profoundly different features than those that are in-house collections. So if you're a company that makes PDFs for engineering documents or healthcare documents, but only one of those things, then those more homogeneous files are going to have very different profiles and distributions of these features than what you're going to find just generally on the web. So those are clearly recognized limitations of this data set. Okay, so in this August crawl of data from 2021, there were about 3.2 billion pages, 360 terabytes total. As I said, there were about 8.3 million PDFs. 6.4 of them, a bulk of them, could be retrieved from Common Crawl without any problems. Another 2 million, though, were truncated in Common Crawl because Common Crawl truncates it at a kilobyte. So we had to go refetch those. So it took us about a month we were being very polite with refetching these files, but it took us about a month to refetch about 2 million files. And you can see that those refetched files were quite big. 6.4 million of the smaller files only took up 1.6 terabytes, whereas the 2 million took up roughly 10 terabytes of data. Then when we stored these by their hashes, that brings us down to about 7.9 million unique hashes for these files, are about 10 terabytes of PDFs. So that's what the bulk of this data represents, and that's what this corpus represents. All right, so size, these are breakdowns of sizes of PDFs. We have about 4 million, about 7,000 are quite small. About, sorry, but if I said kilobyte earlier, I meant megabyte for the truncation of Common Crawl, forgive me. But we do have there are quite a few large PDFs out in the world. Some greater than 100 megs, some slightly greater than a gig. And obviously, we've all run into PDFs that are even larger than that, of course. So geographically, these are kind of from all over the world. We have to be careful with country level precision in geotagging where those URLs are that those PDFs came from. I mentioned in the talk last year that there is a slightly heavier concentration of PDFs in Germany, but you can see that these PDFs do come from all over the world. So in talking about features that we extracted from these PDFs, it quickly became clear that if somebody said, so how, what are the common titles? What are the versions? What are these? What are that? And it really came down to what tools can we use to pull out specific information from the PDFs. And frankly, given how tools change, it was also an issue of not just what tool did we use, but what version was it? So that rather than speaking of, well, this, we had this many version PDFs, we started backing off to, we had this many versions, PDFinfo said we had this many versions of the file, and it's PDFinfo of this version. Which PDFinfo is it? Well, it's Poplar, and so on. So as we know, different tools will find different information about PDFs. We have to be very careful about how we define the information that we're extracting so that we're very precise about what we're pulling out about PDFs. And I end with a cautionary tale on versions of PDFs, which is rather amusing, I think. All right, so this data was gathered in August of 2021. You can see the bulk of the PDFs that had a created date in them that PDFinfo could pull out. The bulk of them were from that year. I was frankly surprised to find that this distribution, if I think about some of the intranet sites that I work on at various places, they typically have a lot more historical data and not this fresh content, but clearly the web has quite fresh content. I should also point out that these are the top 10, but there are also just years that make no sense because PDF. So we have like a couple PDFs from 1900 and so on. But these are the top 10 years that PDFinfo pulled out from the files. So again, these are pretty recent files for when the data was pulled. Now, some other things that we pulled out. How many of these are linearized? Slightly more than a quarter. How many of them are tagged? More than a third. Only about 2% of them were encrypted. Small proportion of them had some kind of JavaScript in them. About 12% had custom metadata. About 60% had XMP. So that's a great source of rich metadata information. A tiny proportion of them had PDFinfo calls user properties. Creator tools. Top creator tool was that infamous creator null. Beyond that, of course, we have some of the more common creators, Microsoft Word, and so on. Writer shows up also. The top 10 titles. Null wins again. Empty string has quite a few, but then we have PowerPoint presentation and so on. So this information is useful for when people talk about the utility of embedded metadata. It can be extremely useful if it is applied with determination by an organization, if they follow good procedures for documenting metadata and storing metadata. But if you're just pulling a bunch of stuff off the web, for a lot of those files, some of that metadata might not be so useful. Now, PDF version, again, I have a couple of slides on this at the end, but these are the alleged PDF versions that PDFinfo pulled out. So mostly 1.4, or tie with 1.4 and 1.7. You can also see that there are a very small handful of 0.0 version of PDFs. So PDFs will say all sorts of crazy things about themselves. And those null versions are probably not even PDF files. In selecting air quotes PDF files from Common Crawl, we did some file identification, but I think we also pulled in PDFs where the HTTP server alleged that the file was a PDF. So we did get a couple of thousand files that weren't actually anything like a PDF. Right, PDF page counts. The bulk of these PDF files only have a single page. Then it goes down, and then we start bucketing them 10 through 19, 20 through 49, and so on. So this gives a fairly decent sense of the distribution of those PDFs in the corpus. This is on the full 8 million corpus. And you can see that a handful of PDFs have more than 10,000 files. About 40,000 PDFs have more than 10,000 pages. So these are some pretty bulky PDFs. Many thanks to Anastasia on our team for doing this visualization of log normalized file size in bytes by page count. So when you log normalize a gigabyte, you get about 20. So that 20 line is about a gigabyte. And this is a traditional box whisker plot. So the line in the middle of the box is the median. The first quartile is the bottom, the third quartile is the top of the box, and then you have kind of the outliers for above the whiskers. And what's interesting to me from this is that you can have a one-page PDF that is as large as a 10,000 page PDF. This will come as no surprise to folks who've worked with PDFs. There is, generally increasing size as you go up, but there are still lots of PDFs that can be very big and have very few pages. The next slide is we bucket the number of pages differently. So here the first box is 1 through 9, pages 1 through 9, 10 through 49, 50 through 99, and so on. So again, a general increasing trend, but you can get there are lots and lots of PDFs that are huge, but have few pages. And this should be no surprise to anyone who's worked seriously with PDFs. All right, so some other questions. We were interested in how many of the files had incremental updates. So we use PDFResurrect for that. It's not perfect, but it's pretty good. We didn't finish the run of PDFResurrect. We just did a sample of 1 million files for this data. Roughly a little bit more than 20% of the files have at least one update. I kind of wave my hands at that one because when Microsoft Word exports a PDF, it will often have one incremental update that's just, I don't know why it's there, but it's not literally an incremental, it is technically an incremental update, but it doesn't point to any different information. So the 22% is caveated that might not be meaningful. When you start getting down to the others, though, I think those are probably more meaningful distributions of incremental updates. We had one file in this 1 million sample that had more than 3,000 incremental updates, which is mind-boggling to me. But again, if you have this many PDFs, one will find some eye-opening things. So that was kind of interesting. We ran Clamav on about 2.8 million of the files. For what use Clamav is, not sure exactly. It found a number of files with JavaScript in them. In the handful that I reviewed, there was nothing that I could find that was malicious about those files. It's just that they happen to have JavaScript. So that's what we found with Clamav. We're considering working with VirusTotal, perhaps, dumping the 8 million files there, seeing what kind of hits we get from them, because they run a huge number of virus scanners on their data. But this is what we did so far for virus scanning. iText, many thanks to the folks at iText for granting us a commercial license for 2 months for the study. They came up with, their tool came up with very similar numbers for the number of encrypted files. They had to fix an XREF on only about 300 files. They had to rebuild an XREF on about 3% of the files. Their tool says that there's a hybrid XREF for about 2 million files, which is kind of surprising. We're going to dig into that one a little bit more. Said that there was an XRF stream in about 4 million files, which was interesting. So those were some of the features that we pulled out of iText. We also used iText to extract text from files, and I look forward to comparing that text that was extracted from iText with the text that was extracted from PDF to text and Tika and some others. All right, so we have some other information. Another tool we used was Apache Tika. I am the chair of that project. For full disclosure, it pulls out some other information via mostly PDFBox. So again, 2% were encrypted, so we're seeing the same number of files identifying encryption across a number of different tools. So that gives us some confidence that that number is basically accurate. A very small number of them had a collection, about roughly 3 million had some marked content in them, and that's very consistent with what we got out of PDFinfo, so that's a good sign. A very small number of them had XFA, and about 60% had XMP. So again, that's correlating well with what we're getting out of PDFinfo, so that warmed my heart. We ran automatic language detection on the text that Apache Tika pulled out, and we limited this visualization to those files that had more than 100 words, more than 100 alphabetic words. Obviously, if it's just a bunch of numbers, we're not going to get meaningful language detection on those files. So this is a subset of files that had more than 100 alphabetic words, and by alphabetic, that's broadly speaking, so that includes CJK. So slightly more than 50% were in English. German was the next most common language after other. Sorry for the sorting on that one, I should have fixed that. And then we have descending order of those languages. The great thing is that with this many files, if you're looking for Portuguese or Polish or some of the languages that are not in the top 10, if you have this many files, you can still find a bunch of files. A small percentage of a very large number is still a pretty good sized number. So this is a fun look at the languages as detected from the text that was extracted from those. Obviously, this doesn't cover image-only PDFs. I did not run OCR on these files. And this is paying no attention whatsoever to the language tags embedded within the PDFs. This is literally just extract the text and run automatic language detection on those files, on the text that was extracted from those files. We were also interested, and I think Duff is speaking about this data as we speak in another session. Many thanks to Peter Wyatt for helping us do a better job of pulling out the PDF subsets. We had about 2% of these allege PDFA of some flavor. Some of the PDFA flavors are just nothing that comes close to a PDFA conformance level that I recognize, but it's only a small handful. When you have this many files, you will find interesting things. A small amount say that they are PDF UA, even though we found a fairly significant number that have tags in them. Obviously, PDF UA is more than just tag structure. A small percentage said PDFX, and a very tiny percentage said that they were PDFVT. And again, to extract this information, we were only looking at the XMP and what the PDF said about itself. We didn't do any assessment of what kinds of data was actually in the files. We did not run VeraPDF or any of the other checkers to look at conformance for these various subsets. One really handy thing about Apache Tika is that it is a framework designed to extract embedded files. So rather than running an individual tool and then running the individual tool, a different tool on the embedded files, Tika is a framework where you specify however many file parsers you want, and then each file parser is responsible for saying, here are my embedded files, Tika, go parse those. So we have, parsers for, I think, more than 100 file formats, and each file parser that can handle an embedded file. So PDF, RTF, HTML can have embedded files, PDF obviously, zip and other traditional container files. Each of those have a bit of code that says, here are my embedded files. Tika, do line type identification on those embedded files, and then run, extract that information, run your parsers on those. So with that, we can get a sense of what kinds of embedded files there are in this batch of PDFs. We did finish the run of Apache Tika, so these are the actual counts on the 7.9 million files. And embedded depth 1 means these are the attachments that likely a human put into the file. And I should be careful to specify what I mean by an attachment. For Apache Tika, and given the way that I ran this, an attached file means pretty much a user embedded file. It's not other file types one would find inside of a PDF. So it's not looking at fonts. It's not looking at images that are used to render the page or inline images. It's not looking at signature stuff or XMP. It's looking at what likely a human attached inside that file as an attached file. So I should be careful to define that. Now, we can, with other settings of Tika, we can pull out some of that information about embedded fonts and about XMP and ICC and those other, and JavaScript, which I didn't run on this run. But we did, for this particular run, this was more like human embedded attached files. So within 8 million files, we found roughly 50,000 text files. A lot of those were like job options kinds of things that weren't really meaningful and were probably put in as part of a workflow, not by a human necessarily. About 12,000 PDFs. We had some MPEGs, we had some Flash files, PNG, GIF, some SVG, and some other files. So those are kind of the files that are embedded at the main level of these 8 million PDFs. Now, then we also looked at what are the file types, ignoring or including the ones that were kind of straight put into the PDF. Those, in turn, can also have embedded files. So any embedded file at greater than depth 0, so that's pretty much any embedded file, what were the attached files there? And there we can start seeing WMF start showing up, as well as Microsoft equation format. So those are embedded file types that show up in Microsoft Office documents. Excuse me. So those are likely reflected in embedded files within embedded files. Okay, so the maximum number of embedded files, so 42,000 PDFs had one embedded file, and so on. 145 had 16 embedded files. We had one file with nearly 4,000 embedded files. At this point, it may as well just be a zip. We also looked at the embedded file depths. So if you embed a file inside of a file and stick that inside of a PDF and so on, the maximum depth we got was 4. I was surprised it was so shallow, but you can see that we have 3,000 files with embedded depth of 3, roughly 40,000 with embedded depth of 2. So this gives a sense of the fact that to get all of the information out of these files, one does need to do parsing on these embedded files and do that recursively. All right. So that's embedded file depth that we pulled out with Apache Tika, and I'll wrap up shortly and open it up for questions in about 2 minutes. So some other really critical stuff that we got out of this is when we run these tools, we keep track of warnings, exceptions, timeouts, out-of-memory errors, crashes, and all those other fun things. And those are really important for parser developers so that they can identify files that are causing problems for their parsers. The runtime exceptions that come in different flavors. Some are from malformed PDFs. Others are more things that should probably be fixed in the parser, like class cast exceptions, null pointer exceptions, those kinds of things. But we've been working with various tool developers, open source and commercial, and sending them reports of how many crashes we've gotten and so on, and gotten some pretty good feedback. All right, some other things, speaking of which, there we go, we've been looking at our crash analytics. So given a particular creator or alleged creator, how many times do parsers fail on that creator? We can do a nice crosswalk of which parsers have the most problems with which creator tools, which is kind of a fun way of looking at parsers and creators, or PDF writers and PDF parsers. So now I'll end on this bit on PDF versions. So you've heard about PDF Association's Peter Wyatt's Arlington model. We ran the test grammar. This represents roughly a 1 million sample on that corpus to get the self-reported version for PDFs, because we wanted to compare that with what we're getting out of PDFinfo. But the other really, really nice feature of, among the many useful things of the Arlington model's test grammar, is that that also extracts not just the alleged version of the PDF, so it's what's in the header, what's in the document metadata, but also what's the latest feature. Because the Arlington model has all of the features by version, it can go through all of the features of the PDF and tell you what is actually the latest feature version in that PDF. What we found is that there's a fairly decent discrepancy between what the version of the alleged version of the PDF is and what the actual features are of that PDF. So in this graph, you can see that the latest feature, when it says 1.7, or a bunch say that they're 1.7, self-reported version, but the ones that say that they're 1.7 typically aren't. There's something else, or more often do you have the latest feature being 1.5 than those PDFs that mention that allege that they are 1.5. So this is just an awesome, just the tip of the iceberg of the power of Arlington and what it will bring to the industry and to parser developers and PDF consumers. This is just it's a tiny thing, but it's just amazing. So this is the confusion matrix of what the PDFs allege they are and what they actually are according to the latest feature as pulled up by the PDF version. The gray middle line is if there's an agreement between what the file alleges it is and what it actually is. So you can see that when a file says that it's 1.7 and when it's actually 1.7, that's only about 10,000 files. When a file says it's 1.7, the latest feature, but the latest feature is only 1.5, that's about 90,000 files. So this is a really just amazingly powerful view of a somewhat trivial but critical feature of PDFs that we're finally now getting to see thanks to the Arlington model and Peter Wyatt's work on that. This is another visualization of that same data where you have the self-reported version along the x-axis, the number of files on the y-axis, and then the latest feature version on z. And if the self-reported version and the latest feature version lined up, there would be a perfect cross line there. But you can see it's just all over the place. So in short, with the Arlington model, we also looked, of course, at warnings and errors. But I just wanted to give just a brief taste of what the Arlington model and the grammar checker can do for you. Buckle up. It will be really, really amazing for what it already is, for what it can offer to validation and understanding PDFs and where how they relate to the spec. So please start using it if you're not already. Please contribute to it. I look forward to continuing to work with Peter Wyatt on it. It is an amazing tool. All right, so with that, next steps. Mostly two key things. We'll continue to work on making it easier to transition. We are looking for a home for that raw data for the 8 million files and the extracted features. And then, of course, we have to document.